All right. Yep. I just started. Yep. I just started recording. All right. Perfect.
The actual. Thanks for joining us.
All right. 4 more minutes. I'm gonna see if I can try this again. Okay. Let's see. 1, 2.
We're starting in 2 minutes. If you go out through here and then it happens.
All right. 2 more minutes and then we can get started. Okay. One more thing.
Checking for errors.
Yeah. I'm trying to see if I can get a 100% accuracy again because I just had it. While I'm waiting for people to join. This is Keros, by the way.
Okay, got it.
Yeah, I'm not doing PyTorch for this. That would be a bit too complicated.
You stop using it, you're done with PyTorch. Hi.
Oh no, just for this. I can use PyTorch for other stuff. All right. Okay. All right, we're getting basically 96%. I guess that's fine.
Okay, guys, we're gonna get started.
As I talk, can you guys go out the room?
Yeah, we're gonna get started. So we can hear everything because all of the mics across the room are gonna be listening. So.
All right. Yep. I'm ready to start. Is everyone joined in?
Yes, sir. I think we're good to go.
All right, perfect. Hi there, everybody. My name's Addy. I'm one of the officers here with the ML Club. Sadly, I can't be in person because I am a bit sick right now. So I'm presenting this from Tucker. So there might be some background noise. Hopefully it's not too bad. This workshop is going to be about sentiment analysis. So we're going to introduce spacey pipelines and then using them to do sentiment analysis. So there's 2 parts basically. And then by the end of this, you should have an idea for how sentiment analysis works and then potentially how to apply it to your own problems. So let's get started. So as I mentioned, the first half of this workshop is going to be on spacey. So I'm gonna start with that. These three cells up here are just downloading our data set. We're using the IMDb movie data set, which is basically just a bunch of reviews about movies, and they're categorized into good reviews and bad reviews, or positive and negative, which is the naming in this particular data set. And basically our task is to classify a review as positive or negative based on the words they use. So this is just downloading our data set, these first three cells up here. So down here, we're just importing all of our libraries. We're using Spacey, we're using NumPy. We're not actually using pandas, but I just import it. And we're using Keras for our actual sentiment analysis. So if you guys are at all familiar with these, this shouldn't be that bad. And even if you aren't, you'll be able to pick up the basics on the way. It should be fine. So the first thing we're going to do is I'm just going to introduce how Spacey works. So this is actually a pretty good visual on Spacey's website. I think you guys can see this page. Can you see the Spacey page or no? All right, I'm gonna assume that's a yes, but I am screen sharing this. So right here is a really nice visual of how Spacey works. So we're given our input text. So in our case, down here we have a sample review, which is just a bunch of words explaining someone's take on a movie. And we're gonna run it through a bunch of different steps to break it apart into tokens and do other types of analysis. So let's start by understanding what each of these things do. So the tokenizer just takes a large portion of words, so in this case, this is like a whole review, and breaks it apart into individual words and clauses and smaller segments like that. This allows us to then work on each one of those smaller segments individually. So to show you guys a demo, right here is the output of our tokenizer. You can see every single word is outputted separately. And to do this, all we had to do was go through, access each of the tokens in this document, and print them out. Once we have our token, oh, do we have a chat? No, we do not. All right. Once we have our tokens, there's a couple other things that Spacey does for us. So for each token, it starts by tagging it. So for example, it could tag things as nouns, verbs, adjectives, etc. That is a really useful feature of Spacey that's available by default. We won't be using it in this particular workshop because we don't need it for sentiment analysis. But based on your problem, you might want it. So for example, if you work with a Twitter data set, you might want to isolate verbs and look for what types of verbs people are using or how strong the adjectives are or something like that. So if you are doing that, the tagger is an interesting thing to look at. Following that, we also have this thing called a parser. A parser just finds out which words are related to one another. And if you wanted to understand which words in a sentence had the biggest impact, you could use that to make those kinds of decisions. For sentiment analysis, we won't be using this explicitly, but again, for certain other problems, you will want to use them. However, the next thing we are going to use in this particular workshop is what's called a stop word recognizer. So up here, we can see that we have all of our words broken apart. These are called tokens. But if we look in here, we have things like or, we have things like the, a. These are words like, yes, they are valid tokens, but they aren't really that important to understanding the emotion in a sentence or piece of text. And that's the problem we're trying to solve. And so what we could do is just remove all the words that don't really add any information to our text. So to do this, we're going to isolate what are called stop words and just remove those from our data set. So to do that, all we're going to do is iterate over this little list right here called tokens. And all we're going to do is call token.isStop. And if that returns false, then we want to keep that because that means that it's not a stop token. Looking at the output here, we have a bunch of different tokens, and all of these are important words rather than things like a and the. Those are the first two things we're going to cover for Spacey. They're actually pretty useful. And just so you guys understand how Spacey is doing this, Spacey is a library that has pre-trained models to do things like tokenization, as well as named entity recognition, and a lot of other things. We do not have to train it from scratch. That's one of the nice things about Spacey. Instead, we can just download their models and use it on our own. So that's what we're doing up here. We're just downloading it like this. So Spacey download English or web. This has been trained on a data set from the web, which is why it's called web. And this is for English. So there's different models for different languages. From there, to use that, all we have to do is do spacey.load and then our particular language model. And our tokenizer and our stop tokenizer are both using NLP, which is just our pre-trained model from Spacey. So we're just creating our model up here, and then we're just going to use it like this. And we can iterate over them to find tokens, and then we can also iterate over them to find stop words and then eliminate those. So those are the first two things we're going to cover with Spacey. Are there any questions so far? All right, let me check chat as well. All right, it looks like we don't have any questions right now. If you guys ever have any questions, feel free to either unmute or just text it in chat, both work. Also, I will be sharing this notebook right after this workshop, so you guys can play around with it and maybe tweak it for your use case. So there we go. We just covered the first two parts of Spacey. To review, this is extracting tokens, which is just iterating over our document, which we declare by just calling NLP on it. And then to get our stop tokens, all we have to do is just call isStop, and that'll tell us if a word is a stop or not. And we're just eliminating all those for data set. So that's all that these two first cells do. Once we do this, there's a couple other things we can do. So we do have a bunch of different like valid tokens in this list right here, which is all of our useful words, so not stop words. But if you look around, there's words that are pretty much the same as one another, but in different tenses. So for example, if you were given something like show and showed, those represent kind of the same idea. And so just to simplify our task, we can just take all these similar words that mean the same thing and turn them into the same word. So different tenses, for example, can be turned into the same base word, and that just allows us to deal with less words overall. There's two ways to do this. The first way is called stemming. And all stemming does is it's just basically a list of endings, like in, for example, running, for example. And all it does is if it finds that pattern, it just cuts it off the end of it. And checks if the word afterwards is still valid. So for running, it would take off the ning, and then it would be left with run. That is a valid way to reduce the number of words using and deal with tenses. But the problem is that it doesn't really understand more advanced relationships between words or anything like that. So there's a more advanced way of solving the same problem, and that's called lemmatization. This uses a lot of tricks from linguistics, and what it does is it actually understands the words and the context and tries to simplify them into a base case using a lot of rules and in many cases ML. So Spacey actually uses CNNs internally. So that's how you would break a particular tense of a word into a base case. This is all implemented for us. It's pre-trained, and so Spacey actually does this for us out of the gate. And so we can actually see how we can do this right down here. So if we wanted to print off all of the lemmas, all we would have to do is call a particular word dot lemma. So I could do something like, let's see, print token dot lemma, and this would print out the particular lemma that we were using. Now, this isn't super useful for us because this does it automatically for us, but if you wanted to extract lemmas, you could do this yourself. So that's just one more thing that Spacey supports. So that's this section covered. And of course, as I mentioned here, Spacey automatically does this for us. We don't need to do it manually. It does it for us because it's a very common task. So now, just to recap, We've covered tokenization. So that is taking a big piece of text and breaking it apart into words. We've covered removing stop words, which is taking out useless words like and or. And then lemmatization to take all those words and boil them down to less words. So that's what we've covered so far. Now that we have this list of words, we're going to solve our next problem. And that's basically, how do we actually understand the emotion in a review or the sentiment in a review? That's our problem after all. So we want to use a neural network for this, and that's mostly because neural networks are able to understand really complex relationships between words and also can make decisions based on a lot of different parameters. They're more sophisticated than basic algorithms that we've covered, like linear regression and log regression, and they're actually well suited to solve this problem. Now, there is one thing we have to solve before we can use them, and that is, how do we take a word and represent it as a vector? So there is a lot of different ways to do this. You could represent it based on how frequent the word is, but we're going to use a technique known as word embeddings. So just to do a quick overview, a word embedding is an algorithm that takes a word and encodes it as a bunch of numbers. And that list of numbers tells us things about its context, its meaning, and you can actually compare the embeddings for two similar words like red and blue, and they'll show up to be very close to each other. They're very similar. And that's because the context around them is also very similar. They're both colors. They're both used in similar cases. So word embeddings allow us to take a word and turn it into a vector. Once we have it as a vector, we can actually use it with all of our fancy algorithms. Now, we're not going to cover exactly how these embeddings are implemented, and that's because implementing them from scratch is actually rather complicated. There is going to be a link in the Notion that goes over how to implement word2vec, which is the most common word embedding from scratch. But for right now, we're actually going to fall back on Spacy once again, because Spacy also does word embeddings for us. So right down here, this is actually a demo of how this would work out. So all we're doing right here is we're picking the first word in our non-stop words. This is homelessness. And we're printing out the vector that Spacy gave it. This is just a bunch of numbers, as you see, that's 96 long. And to us, it might seem like it doesn't make much sense. Like, why is it a bunch of numbers? What matters, however, is that these word embeddings do actually mean something. They are tied to each other, and similar word embeddings do actually correlate to similar words. As long as that's the case, we can use these vectors without knowing what each attribute means. In fact, in most word embeddings, you can't really isolate what each individual row means or each column means, because the ML model did it by itself. We don't really know what it's trying to encode. So this is a vector for homelessness. We can also do, like, for example, if I did 1, we'd be getting the vector for issue. So if I hit this again, we get a completely different vector. This vector now represents issue, which is a different word. And again, we can't really tell what it means just by looking at it, but it is similar to words that are similar to issue. So potentially the word problem might have a similar word embedding to the word issue. So that's what this basically is. It is just a representation of our word as a vector. Now that we have our vector, we can use this in a neural network. Are there any questions so far? I think I heard someone's mic go off. All right, chat is also empty. Again, feel free to type things in chat if you guys need help with anything. All right, perfect. So now that we've covered this concept of taking words and representing it as a vector, let's move on to our next major segment. And that's actually using these vectors to solve our problem, which is sentiment analysis. So the first thing that we're gonna do, this is actually something that all of you will have to do for using the Twitter data set, is actually load your data into your notebook. So obviously this is not gonna look the same as Twitter because you guys are using JSON. IMDb actually looks a bit different. So this folder right here is the IMDb data set. If I go into here, we see train and test. So this represents train data and testing data. And inside of them, we have 3 folders: negative, positive, and unsupervised. We're only gonna use negative and positive, and those are our 2 classes. If I open up negative and then click on one of these files, so wait for it to load up. if I click on one of these files and move it out of the way, you can see that because it's in the negative class, this review is rather negative. I mean, it starts off with saying this film lacked something, and throughout the entire review, they're providing a negative sentiment about the movie. That is why it's in the negative class. And that's true for all the data points in negative class, and for the positive class, it has positive sentiments. We're trying to understand based on the words they're using, is it a positive or negative sentiment? So let's start by looking at how we're loading our data. So all we're doing here is we're reading each file and then loading it into a string. So we're just defining our function load. Our source is just which folder we're using. So train just means we're using our training data set, and then test means we're using our testing data set. And then label, in this case, is NEG. That means we're looking for negative labeled data points. If you wanted positive, just pass in pause, and it would look at the other folder. And actually, this is shown right here. The first thing we're doing is we're just finding the folder name. So we're taking the ACLLMDB, which is the folder of the whole data set, and we're adding on whatever portion of the set we're using, so in this case, train. And then finally, we're adding on our label, so that's pause. So this is just going to represent our folder. Once we have our folder name, we're going to figure out what files are in here. So if I was to do this, so print files, hit enter, you can see right down here that we have the names of every single file in this data set. So all of these are negative data sets, so rather negative text, which represents negative reviews. And if we change it to pause, we'll get positive reviews, obviously. Now that we have the names of all of our files, we're now going to select one of them or select any number of them. So all we're going to do is say for I in range count. So that's we're going to select count number of elements. We're going to pick one of the file names. We're going to open it. So that's just to open it for reading. And we're going to read it into this string right here. So file str. And then we're going to close our object. So if I was to print off FOBJ file string right now, enter, and look down here, you can see right here that we have the text for a negative review. So it says, I finally got to have a look at this experimental Lynch short, and unfortunately it wasn't worth it. So as we can see, it's got negative sentiment to it. Once we have our string, there's a couple cleanup things we have to do. First of all, for some reason, this data set has these breaks written into it. So we're just going to remove those, and we're going to replace them with new lines. So they're just easier to work with. We're then going to strip it, which just means getting rid of white space. So if there's extra spaces or anything like that, strip will get rid of it. Finally, we're going to figure out what label our data set has. Now, we are given the label up here, but as you guys might have remembered from our lectures with Dr. Jaski, we actually want to represent these as either a 0 or a 1 based on if it's negative or positive. So the way we're going to do that is we're going to find a Boolean, is the label positive, and we're going to convert that to an integer. What that's going to do is it will return 1 if the label is equal to POS, so positive, and 0 if it's negative. Those are our two classes in this case. Then we're just going to append these to our list, which is the list of all the things we're finding so far, and we're going to return the whole thing. So if we look right here, we're returned an array. The first one is our string, and then our label. So in this case, 0 because it's a negative class. So that is what the load function does. Again, for the Twitter data set, you'll have to implement something similar to this, but this is how it's going to work for the IMDb data set. So now that we've gone over how we're going to load data, let's next talk about converting our text to vectors, because as of right now, we're still dealing with text data. We want these as vectors. So the first thing we're going to do is we actually have to introduce a problem we have to solve. And that's that for neural networks, you have to input things with a fixed size. You can't input one data point with 200 words and another with 500 words. Every data point has to have the same number of words in them. Now, to make that work with our data set, all we're going to do is set a fixed size. So in our case, we're saying this the word count equals 400. If we have less than 400 words in our data point, we're just going to add zeros to the rest of the vector, and that just means that it's empty. That just means there's no extra words. If it's longer than 400 words, we're just going to cut off every word after that because it's not super useful. We want every one of them to have the same number of data points, the same number of rows. And so we're just going to use 400. That should be enough rows for us to make a decision on this. So we define our function right here. So this is converting review strings to vectors. And we define our output array. And all we're going to do is going to iterate over every single review. So every single one of these strings right here. The first thing we're going to do is, as we did up here with this sample, is we're going to run spacey over the entire string. So we do that right here. So doc is equal to NLP doc string. All this is going to do is run our entire spacey pipeline over this string. So that involves tokenization, stop word removal, all that stuff. The next thing we're going to do, as we saw up top, is we're going to actually get the vectors for every single word. So the way we're going to do that is I'm just going to call word.vector for every word in our document. So in other words, this will go over the entire review string and call dot vector on every single word. And that's going to be returned as a vector, as a list of vectors. So this, the length of this is based on how long that particular comment was. And we're going to add that to our output array. So that is our return value for this function. And this is the important part. We're going to use this function from Keras called sequence.pad sequences. What this is going to do is guarantee that all of our vectors have the same number of rows. If they have less, it's going to add zeros for everything else. If it has more, it's going to cut it off. So the way we're going to do this is we're going to call on review array. We're going to set max length to word count. So that means that we're targeting 400 words. And we're going to say data type is float 32. That way we don't convert everything to an integer on accident. Now, as we see down here, the first about 100 rows are full of zeros. And that's because this particular review isn't that long. It falls short of the 400. So the last couple rows are actually our word embedding, so our vector. The top 100-ish rows are a bunch of zeros. That's just to say it's empty. So that is how we're going to convert all of our reviews into a set of vectors that's 400 long. Now that we have a list of vectors that's 400 long, we can actually perform sentiment analysis on this. So let's take a look at this cell right here, which defines our entire Keras model. So up here at the top, we define this thing called samples. Samples is just how many reviews we want to learn from at one time. So basically, if samples is 200, we're going to grab 200 positive reviews, 200 negative reviews, and teach the network how to categorize those 400 reviews accurately. And it'll work in batches of 400 at each time. And loops is just how many different batches do we want to look at. So in this case, we're going to grab 200 positive and 200 negative reviews per batch, and we're going to have 4 batches. So we're going to look at 1,600 reviews total. And that's going to be all the training data we need to train our model. So this right here is our model. This is using the functional interface for Keras. So all we're doing is we're defining our inputs. So this is the shape of this is word count 96. As we said before, we want every one of them to have the same number of rows. So that is defined up here with word count. 96, this might seem like a weird number. The reason for that is the length of our spacey word vector. If you look down here, when we print out the length of each vector, we get 96. That means that Keras needs to be able to take in vectors that are 96 elements long. And so that's how we define the shape up here. Word count 96. That means we have 400 words per review, and each word has 96 numbers associated with it in a vector. Now, we also want to treat the entire review as one contiguous block. And so to do that, we're just going to run layers.flat. All this does is that it takes our 400 by 96 rectangular matrix and basically turns it into a 1 by 38 400 matrix. All that does is it treats the entire piece of text as one input. Then we're just going to do a standard neural network on top of that. So we have a first layer, which is 250 neurons, a second one with 100 neurons, and then a third one with 10 neurons, and then our final activation layer. So this is going to have one neuron with a sigmoid activation. We covered sigmoids during our lecture. All it does is outputs a number between 0 and 1. And the reason we want that is because those are the only two classes we have right now, 0 and 1. 0 means negative, 1 means positive. Now, we're going to define our model right here. So model equals Keras.model inputs outputs. That's going to tell Keras this is where you put the data in, and this is where the output comes out. And if you run summary, it tells us what our model looks like. So we have all of our layers listed off right here. Now, the next line we have right here is just telling Keras how do we want to optimize this. So we're running .compile. The optimizer is just what optimizer function we want to use. We cover gradient descent as part of our curriculum, but Atom is actually a very good optimizer for neural networks. So Atom is what we're using here. Now for the loss function, this is actually a different name for the log loss function we covered for logistic regression. It's really good for problems where the outputs are either 0 or 1, and that is what this loss function is designed for. So that's why we're using it. We have two classes, 0 and 1, and so this loss function makes perfect sense for us. Finally, we pass in metric equals accuracy. All this says is that we want to optimize our model for the accuracy on the current batch of data points. So that's self-explanatory. Now here is our actual training loop. As I said before, we're going to run 4 times on 4 different batches of positive and negative reviews. So that's shown with this for loop right here. So 4 IN range loops. Inside of each one, we're going to grab 200 positive and 200 negative reviews. And then before feeding it into our neural network, we're going to take all of our positive and negative reviews and put them into one list. So that's what we're doing right here. We're concatenating our strings together. So we're concatenating our X's, which are our actual reviews, and our Y's, which are either 0 or 1, which represent negative or positive. We're then going to do what we did before, which is to convert all of these strings and these words into vectors so that our neural network can actually train on them. And finally, we're just going to run .fit. .fit will actually train our model, and that will allow us to make predictions. So if I'm to run this right now, it'll take a second to run. So let's take a peek. Let's see. Oh, I think I left a print statement up here somewhere. Yeah, get rid of that. Stop this right now. If I run this, we're going to start outfitting our model. So, oh, there's another print statement up here. Let's see. Where is that print coming from? All right, let's go down. Oh, are there any questions or no?
No, just Control F audio.
I'm so sorry.
It's working now. I just suggested Control F.
Okay, sounds good.
But yeah, you got it. It's working.
All right, yeah. So up here is just a bunch of our reviews printed out. Down here, we actually see the Keras training loop. So it's running 20 times on each batch of 200 positive and negative reviews. And we can see that we're actually getting really good accuracy, about 97%. This is going to run 4 times over 4 different batches. And that way it's able to generalize onto new unseen data points. So this is going to take a second to run. So yeah, it's printing out our next set of reviews. And then it should start fitting rather soon. And once that's done, we can actually go ahead and see what our real world accuracy is. So this is going to take a bit of a second. So are there any questions right now? All right, checking chat as well. All right, it looks like no, there is not. All right. If there are any questions, feel free to let me know because I'm still just waiting on this fitting loop. All right, and we can see the accuracy.
There is a question. Yeah, if you want to come up here so that he can hear you. There's a question on you.
Oh, yep. All right, perfect.
Just over here. Come up here and then ask it from because yeah, I didn't realize the audio was going to be kind of quiet back there.
Yeah, the mic's not that great.
How do they know the difference between positive and negative?
So for us, we actually are given the labels. So the labels are 0 and 1, and that tells us which one's positive and negative. So that's in this little list right here. So if I print off Y, or actually if I print off Y down here, let's do this one sec. I will actually have to wait for this training loop, but I can demonstrate that in a second.
How did they get labeled?
I'm sorry, what?
What makes something positive? What makes something negative?
So the actual data set was compiled by the researchers who made this data set. So it was manually labeled by humans, and then they were given the labels after the fact. We're just trying to train and network on that. Sorry. I'm sorry. I'm having trouble hearing you.
I'm gonna mute my this mic, and we're gonna do it through my laptop because clearly
Okay.
the big mic is not working.
Yeah, sounds good.
Oh, that's not fun.
Can you hear me?
Yes, I can.
Why is that causing issues? Give me 1 second.
Can you hear me?
Yes, I can. Oh, you're muted once more. There seems to be some echo. I'm not sure who's causing it.
So how did the people come up with positive and negative?
So the positive and negative just represents whether or not that's a favorable or non-favorable review. So they would just read through it just manually.
Do you think there's any problems with that?
It is very expensive to do that. There are some new tricks in semi-supervised learning to be able to label them with less data, but this data set is pretty old, and so back then the best way was just to manually read it.
Right.
Do you have any advice for people that are looking to label data? Is there any way that you would automate it, or do you think that training a model off of other negative data could be applicable to doing sentiment analysis on this one?
So if you were given, is the question how to use a data set without labels pre-made?
No, just do you think that this data set could be used for example on other positive and negative data sets? What resources do you have to recommend to people looking to work with not the IMBD one, for example?
So this model that we're training right now should be able to generalize to non-IMDb reviews, because we are testing with a lot of different ways of wording it, and so it should generalize. If you want, there's other data sets on sentiment analysis, and if you train a model on all those mixed together, you should be able to get a model that can do sentiment analysis on any text. IMDb is a good one. There's a couple of data sets that I can send in chat in a second if you give me a sec to look those up. But IMDb is a big one. I know Twitter actually has a sentiment analysis data set pre-made, and there's a bunch on Kaggle. So if you want to look at those, you can use those to train a general model. Is that the question you guys are asking?
Yeah, that was my question. My fault.
Okay.
Did that help at all with answering your question as well? Sure.
I feel like I want to ask another. Can I ask another?
Go ahead.
Yeah, go for it.
You were training with a balanced, even number of positive and negatives, right?
Oh yeah.
Why are you doing that?
In my case, it's just because it allows us to get a smoother training output. But if you had an uneven number of positive and negative classes, you could subsample the majority class or super sample the minority class, and that would let you basically generate more synthetic data. That's one way of doing it. But you do get some trade-offs there that you have to play with.
I'm just wondering, why are you balancing it at all? Just why not just train on a bunch of positives and just a little bit of negatives? Does that affect it?
That generally leads to way lower accuracy because it'll just optimize for the positives.
So is the real world balanced? I mean, is
the real world is not balanced, but there are tricks to feed them into a network as if it was balanced data.
Is that important for it to be balanced?
Yes. Yeah, wait, sorry, say that one more time.
Is it important to have balanced data?
Very, because the way these models work is they're trying to optimize cost. But for example, right, a very extreme example, if you had a data set with 99% of one class and 1% of another, a pretty cheap way to get a good accuracy is to just say all of them are the majority class. Because that way you'll only have a 1% accuracy. You'll still have a 99% accuracy. But if the goal is to classify that 1% accurately, that's not going to be very useful. So you would want to balance your positive and negative labels.
I mean, that does sound like a realistic situation where you might only want to classify like 1% of something.
Yes, so there are a couple ways to do that. One of them is if you have data that is very close together, like you can graph it as close together, you can use something similar to like a k-nearest neighbors algorithm to generate new points in that same region. And that'll let you basically create synthetic data, but that doesn't always work. If that doesn't work, you might just have to train with that small amount and then take small batch sizes of the majority class and keep training it. Beyond that, there are some tricks in semi-supervised learning to solve that, but I'm not too familiar with those.
Yeah, hey, thanks. This is a good presentation, man.
All right, thank you. If anybody else has any questions about this or anything else, feel free to ask.
Anybody else?
And it doesn't even have to be about sentiment analysis. If it's just about basic ML, feel free to ask. Okay, so we just trained our model. If I run it now on our testing data set, let's see what our accuracy is. Oh, let's see. It could take a bit to run it. Okay, so we're still converting our words to vectors. This will take a bit of a second. Let's see. Oh, let's see. It just ran. Okay, we have a 96% accuracy. That is actually really high for this particular architecture. Frequently, you use convolutional or LSTM models for this, but this particular data set's not that hard to classify. So, and 96 is doable. So that's how you can do sentiment analysis with MLP. I'll dump this in the chat right now and on Discord so you guys can play around with it and change it for your own tasks. But yeah, hopefully that was helpful. And if you guys have any questions, you can either ask now or you can Discord message me. I'll type my Discord username in the Discord as well. All right. Any last questions or no?
We're all good?
All right, sounds good. I will put this in the Discord right now. I'll be hopping off right now.
Thank you so much, Adi.
All right, awesome. Good luck with your guys' hacks. Hopefully you guys win. And even if you guys don't, hopefully you guys learn a lot because this is gonna be awesome. And also I'm looking forward to see what you guys build on Sunday. All right, guys, see ya.
See you, Adi. Thank you.